Hi there, welcome to this talk on quantum algorithms for matrix scaling and matrix balancing. My name is Nieuwboer. I'm a second year PhD student at the Korteweg de Vries Institute and at QSoft at the University of Amsterdam, and this is based on a joint work with Joran van Apeldoorn, Sander Gribling, Yinan, Michael Walter and Ronald de Wolf. You can find the full version of our paper on the archive. Let me first give you a brief outline of this talk. First I'll tell you about matrix scaling, then about the applications of matrix scaling and matrix balancing. Next we'll go into Sinkhorn's algorithm, a popular algorithm for solving matrix scaling problem. Next we'll talk about the more prior work and our results and how they fit in. Then later on we'll get to our quantum version of the Sinkhorn algorithm and a quantum lower bound that we prove. And lastly, I'll give a brief summary and I'll sketch an outlook for some future research directions. So let's get the matrix scaling. So the idea is as follows. I give you a matrix A, it's an n by n matrix with non-negative entries. Then I define the row and column sum vectors of this matrix as follows. The ith entry of the row sum vector is just the ith row sum of the matrix, and similar for the column sum vector. Then the matrix scaling problem is the following. Given two target vectors r and c, both of length n and a precision epsilon, I want you to find positive diagonal matrices x and y, such that if I look at the matrix B, which is given by left multiplying A with x and right multiplying A with y, then I want B to have row sums approximately R and C and column sums approximately C, where approximately means epsilon close and L1 R. So the main goal of this talk is to explain to you how to get a quantum speedup for matrix scaling. Right, let's look at some applications of this problem. So scaling, for instance, was used to get a strongly polynomial time algorithm for approximating the permanence of non-negative matrices, the first of its kind. This is a very nice application, I think. It's also related to bipartite perfect matching. Next is an application which is more recent. It can be used to quickly approximate optimal transport plans in machine learning, where you have a starting distribution and a target distribution. You want to find a joint probability distribution which marginalizes to these two distributions, which is a transport plan, and you want to find one such which has minimal cost. You can approximate such a plan directly by scaling a particular matrix. Furthermore, the first application that I know of was actually in maximum likelihood estimation for log linear models. This is also where the Sinkhorn algorithm, or the many other names it has been called by, was first developed in. Next I'll tell you a bit about some applications of matrix balancing, which I'll only introduce later. So balancing, for instance, is literally used every day because it's used to precondition linear systems for numerical stability, and it's enabled by default in LAPACK and MATLAB for singular value decompositions. So this is literally applied every day. Furthermore, you can also use it to approximate min-mean cycles in weighted graphs. So let's get the Sinkhorn's algorithm. So our goal was to find positive diagonal x and y such that my row sums of xay become r and my column sums of xay become c. Now, the idea is that left multiplying with diagonal matrices allows me to rescale my rows, whereas right multiplying with a diagonal matrix rescales the columns. So that means I can rescale my rows and my columns however I want. In other words, satisfying either of these constraints exactly is actually easy, because I can literally just pick the x that I need to get my row sums to be correct, or the y that I need to pick my column sums to be correct. But of course, satisfying either of these may disturb the other constraint again. Now Sinkhorn's algorithm just alternates between these two. So it's literally alternate between rescaling the rows and columns. Now the surprising thing is that it actually converges whenever A is scalable, and more about that later. We'll first look at that at an example now. So suppose that my targets were actually R is 1, 1 and C is 1, 1. So I want to scale to a doubly stochastic matrix, that's what it's called. And suppose I want to scale this particular matrix A. Then in the first step we would want to normalize the rows to 1, and which we can do by dividing by the row sums, or the current row sums. Now when you do this you get the matrix 1, 3, 2, 3, 1, 0. Now you want to divide by the column sums, you get another matrix. And if you do this for 2t steps, then you will get a matrix whose row and column sums are roughly 1 up to an order 1 over t error. So you can see that here it converges. But actually what's even true is that synchronous algorithm even converges when A only when A is only asymptotically scalable, i.e. it's epsilon scalable for every epsilon larger than 0. Now how do you check this? Well, I will give you an equivalent condition now, which is the following. It actually only depends on the support of A. This is very nice because the support of A is usually easier to describe. And in fact, A is asymptotically scalable to any RC in the convex hull of the vectors EI, EJ, such that Aij is not equal to 0. So for any vector in the support, I add a vertex to a polytope, and any pair R, C which is in that polytope can be scaled to. As a simple example, suppose I look at the matrix A is 1, 2, 3, 0. Then my polytope would have 3 points, given by these 3 points. And for instance, the vector 1 half, 1 half, 1 half, 1 half is in the convex hull. So therefore A is actually scalable to uniform marginals, as we would call it. From this condition you can also prove that if A is entrise positive, then it's going to be asymptotically RC scalable, no matter what RC is. And last, as a nice connection, if R and C are the uniform marginals, or the uniform distributions on N, then A is actually asymptotically scalable to these R and C, if and only if its permanent is larger than 0, which is true if and only if A is the weighted adjacency graph of a bipartite graph, which has a bipartite perfect matching. Good. Now let's get to some prior work and what our results are. So I want to assume that A has m non-zero entries. It's subnormalized in the sense that its entries sum to less than 1. It's asymptotically RC scalable, and I want to fix the normalization of R and C by requiring them to be normalized in the 1 norm. Then what's known classically is that if I give you a precision epsilon, then you can find, depending on the matrix, you can find these scalings in particular times. For instance, in the entrise positive case, which is where every entry is strictly larger than 0, you can find, using the classical Sinkhorn algorithm even, an epsilon scaling in time order n squared divided by epsilon. Whereas for general matrices, you can find one in time m over epsilon squared, so it has a slightly worse epsilon dependence. There are also rather sophisticated second order algorithms for solving this problem. These rely on graph sparsification and Laplacian system solving, but these can find, at least for entrise positive matrices, so epsilon scalings in roughly linear time, with a logarithmic 1 over epsilon dependence. And linear here just refers to being linear in the input size, which is n squared in the entrise positive case, and m in the general case. Furthermore, you can also find in sort of almost linear time in general scalings even for general matrices. Now, what are our results? We prove a quantum speedup for a quantum variant of a Sinkhorn algorithm. Namely, given oracle access to our matrix A, we can find an epsilon scaling in time n to the 1.5 over epsilon to the third if the matrix is entropized positive, and in time square root mn divided by epsilon to the fourth otherwise. So the thing to note here is that these complexities for constant epsilon are sublinear in the input side, which is n squared or m, so you cannot hope to do this with a classical algorithm. One could wonder whether you can do even better. Unfortunately, this is not the case. We prove a matching quantum lower bound in the sense that for constant precision scaling, you need at least square root mn quantum queries to the entries of your matrix. Alright, so these are the results that we have on the scaling side. Now let's get to balancing. So in balancing, what you have is you have an n by n matrix, again non-negative entries. It has m non-zero entries, and I want to assume that it has zeros on the diagonal for a technical reason. Then what is the matrix balancing problem? Well, given a precision epsilon, I want you to find a positive diagonal matrix X, such that if I left multiply with X and right multiply with its inverse, then I get an epsilon balanced matrix, which means that its row and column marginals are approximately the same in L1 norm. And you can ignore this part, this is just a normalization. Okay, so this looks structurally rather similar to matrix scaling, because I just want to do something with the row and column sums. And indeed there is an analogous algorithm, which is called Osborne's algorithm. And I've given you a randomized variant here, where you do the following. You just pick a random index I, and what you do is you update xi exactly so that I of your new rebalanced matrix is equal to ci of your rebalanced matrix. So there is a nice closed form expression for such an update for xi. What's surprising is actually that convergence of this algorithm was only shown in 2015, and by now it's known that the runtime is roughly m times the minimum of d over n1 over epsilon divided by epsilon, where d is the diameter of the underlying directed graph. Furthermore, there also exist second order methods with a similar complexity as for matrix scaling. Now, what is our contribution in this area? So we show that there also exists a quantum speedup for matrix balancing. Namely, we show that a quantum variant of randomized Osborne, given oracle access to A, can actually also find an epsilon balancing in square root mn over epsilon to the fourth. So we have a trade-off between the input size and the precision, compared to classical algorithms. I do want to warn you that the quantum analysis of this algorithm is much more difficult than in the classical setting, because we cannot test whether our matrix is balanced in every iteration. Now, let's get to the meat of quantum synchron. What's quantum about it and how do we make it? So I want to assume that A is asymptotically RC scalable and we're given some precision epsilon larger than 0. Then the quantum synchron part consists of basically two contributions. So first we show that you can get a quantum speedup for implementing the iterations themselves. However, this comes with a cost, namely that we make small errors which are relatively large to the ones you would make with a classical algorithm. And then to counterpoint this, we have to bound the number of iterations in a new way by giving a robust version of the potential argument that one would use for a classical algorithm. So let's get to the iterations. So in every iteration I want to test whether the matrix is epsilon scaled, and I want to update my x or y if this is not the case. So the expensive operations in this process are basically computing the row or column sums of the rescaled matrix. Classically, you can do this in time order n per row or column, which would give you, you have n rows or columns, so you would have a time of n squared per iteration. However, quantumly we can do something slightly faster. Namely, if I pick some delta, which I use as a multiplicative precision parameter, then I can implement these synchron iterations in quantum time n to the 1.5 divided by delta, where I use 1 plus minus delta multiplicative approximations of the row and column sums for my updates. The way that we achieve this is by computing these row and column sums using quantum amplitude estimation, and each of these sums we can compute in time squared n divided by delta. So what's to do next is to find such a good choice of delta, and to then bound the number of iterations. However, I do want to warn you that this is rather involved to make precise, because we have to use finite precision arithmetic everywhere, and the x and y are typically exponentially large in n. So we cannot even write down the entries of x, a, y typically. Or we cannot hope to. So let's get to the iteration bound. So what you would do classically is the following. You would look at not x themselves, x and y themselves, but at their logarithms instead, because this is slightly easier to work with. Then we have the following potential function, f of xy. So x and y are now just vectors of length n in Rn. So I have a weighted sum of my matrix entries, weighted by exponential of xi plus yj. And then I subtract an inner product of r with x and the inner product of c with y. Now why is this useful? This function is actually convex in x and y, and its gradient is 0 if and only if the matrix xay is exactly RC scale. So minimizers correspond to exact scalings for this potential. So that already gives a hint as to why this is useful. Now, whenever you have a potential function or a potential argument, you need two ingredients. You need a potential bound, which tells you how much can your potential drop, and you need to know that if your matrix is not epsilon scaled, then it drops by a certain amount. So that you must become epsilon scaled within a certain number of iterations. Now the potential bound is as follows. If all the non-zero entries of A are at least some mu larger than 0 and the matrix is subnormalized, then actually your potential cannot vary more than log 1 over mu from the starting point. And this was known for A, which were exactly scalable, but we show that it also holds for asymptotically scalable matrices. Now, okay, we have our potential bound. So now we want to show that if our matrix is not epsilon scaled, then it decreases by a certain amount. If we can lower bound this, then we can show that we cannot have this condition for too many iterations, because otherwise our potential would drop too much. So the question is, how much does f decrease per iteration? Now, if you use exact row sum computation, as one would in a classical setting, then you can show that the potential drops by exactly the KL divergence between your current row marginals and your target row marginals. This is at least 0, because the KL divergence is always non-negative, and you can show that it's at least a constant time epsilon squared if your matrix is not epsilon scaled by Pinsker's inequality. Now, what is our contribution? We show that if you, instead of using exact row sums, you use multiplicative approximations to the row or column sums, then you still get a progress of roughly epsilon squared minus delta. So this gives directly a good choice for delta, which is epsilon squared over 2, because if I make this choice, then in every iteration my potential drops by epsilon squared over 2, and it can only drop by the logarithm of 1 over mu. So within log 1 over mu iteration over epsilon squared iterations, I must become epsilon scaled. In other words, for this choice of delta, I get a total quantum time of n to the 1.5 divided by epsilon to the 4th. So these were the two main ingredients for showing that quantum synchron works. Now, let's get to our lower bound, because one might still hope that there exists a quantum algorithm for scaling whose n or m dependence is lower than square root mn. However, we dash this hope by showing that there exists a universal constant epsilon 0, such that any quantum algorithm that scales with this particular precision to uniform marginals uses at least n to the 1.5 queries if the matrix is dense, or square root mn queries if the matrix is sparse. Now, one might wonder how we prove this lower bound. So we reduce it to a relatively combinatorial problem, which is learning permutations modulo 2. So the idea is the following: I take a permutation of n symbols, then you can show using an adversary bound that finding with probability at least 2/3 the output of the output sigma j for every j modulo 2 takes at least n to the 1.5 quantum queries of the form is sigma j equal to I. And it's even true that this holds for recovering a constant fraction of these sigma j's modulo 2. Now, how do we reduce this problem to matrix scaling? So what you can show is that there exist little 2x2 matrices, B0 and B1, such that from approximate scalings of these matrices, you can tell whether you had a B0 or B1. Then what you do is you construct a matrix A, which is now a block matrix with n by n blocks, each of size 2x2. So the sigma j jth block will be b sigma j modulo 2, and the rest of the blocks are just 0 blocks. So what this means practically is that if you have, say, the free cycle 1, 2, 3, then you look at the associated permutation matrix, you replace the ones in odd rows by b1, and the ones in even rows you replace by b0. And the rest of the zeros you replace by a 0 block. Then you can show that from a constant precision scaling of this new matrix A, you can correctly recover a large constant fraction of these sigma j's modulo 2. And therefore, if you could solve matrix scaling more efficiently than order n to the 1.5, then you would get a contradiction, because we can use it to solve this learning permutations modulo 2 problem. Alright, so that's it for the lower bound. Now we will get to a brief summary. So what we've shown is you can get a quantum speed up for matrix scaling and balancing, at least in the constant precision regime. We also proved that we can't do any better in the constant precision regime, by giving a matching quantum lower bound for matrix scaling. So there are a few open questions left. Of course, one can wonder about whether there are specialized quantum algorithms for any of these nice applications that I mentioned. What's more is there also exist many generalizations of matrix scaling, like operator scaling, tensor scaling, operator scaling which you could view as a quantum version of matrix scaling. And it would be very nice to find out whether there are quantum algorithms for these generalizations. And lastly, on the side of improving these results, we have an upcoming work with Sander Gribling, where we show that a query lower bound of omega m should hold in the 1 over poly n scaling regime, and we've also proved some better upper bounds. And with that, I'd like to thank you very much for your attention.